Hello everyone. We'll start with EEEE lecture number 38 today. EEEE lecture number 38 live, and today's date is 24/24. Okay. So I think I want to just clarify one point which we have discussed in full wave center tab rectifier. Okay. So in this full wave center tab rectifier, if I have a block like this, and if I apply my input over here like this, what will be my output? Yes or no? Any point of time, two diodes are on. So this is my input and this is my output. And we have derived the expression for VDC, IDC, VRMS, IRMS, efficiency, ripple factor. Yes or no? Everyone. I've also talked about the PIV rating. So PIV rating, there is a slight correction. PIV rating for the diodes. There are two diodes used over here, right? T1 and D2. So PIV rating of the diode is 2 VM, not VM. I'll show it to you how. So if you see the screen, so at one point of time only one diode is on. So when the one diode is not on, the VM will be V secondary by 2. Okay. So V secondary voltage will be appearing across the diode. So that will be twice VM, not this thing. Let me show you the waveforms. I don't know whether, yeah, here I have drawn it. See. So voltage across the diodes VD2 and VD1, it's minus 2 VM. So that correction we have to make. Rest everything is fine. So PIV rating of diode will be 2 VM. Only in case of center tap, because what happens is, why it is so? Because across the secondary the voltage is divided into V secondary by 2, V secondary by 2. Okay, alright. And whenever one diode is off, V secondary by 2 voltage appears. So what will be V secondary voltage appearing across the diode? It will be twice VM. Understood this? So this is one correction which we have to make. I think I have document 37B. Here I have covered, no, here I have not covered that. 37A I guess. No, this was done in the class I guess. Okay, so please make sure that you correct it. Alright. Now this is full wave center tap. Full wave bridge rectifier also we covered, right? And we found out that the for a full wave bridge rectifier, okay, you get the same output, but here the VDC formula, IDC formula, VRMS, IRMS, the efficiency and the ripple factor is all same as this. Okay, but the PIV rating of the diode in full wave bridge rectifier is not 2 VM, it is VM. Okay, so we will see the waveforms over here. I think we have discussed the waveforms in the last class. Let me show it to you. Here it is, right? So we have drawn the waveforms, but not the waveforms of the across the diode, but it's 2 VM. Just remember it. All right. Okay. Bridge rectifier. Let me show if I have drawn over here. So if you want to see the the wordings of everything, then I will be sharing this document. You can have a look at it. Okay. So here it is. See VM. So voltage across the diode D1 and D2 when they are on, it's minus VM only, not till my 2 VM. So this is one of the facts which I wanted to discuss. Now, if I wish to compare all the three configurations, I can do that. So this is half wave rectifier. Then we have full wave center tap rectifier. Then we have full wave bridge rectifier. Okay. So if I want to compare the all three configurations, I can do the comparison easily. So I am not giving the exact answer, I'm giving you the point of basis where you can compare. So first thing you can compare is circuit diagram. Okay, so you need to draw the circuit diagram for full wave bridge, full wave half wave rectifier, and a full wave center tap rectifier. Agree? Okay. Now next, how many diodes are used over here? One diode used, correct? Here we used two diodes, and here we have four diodes used. Okay, agree? Next point of comparison will be what will be the average value, V out average or VDC value. Can you remember? Can you tell me here how much it is? We have derived now. Just a few days back we have derived this. Can you tell me how much is the value? Yeah. For half wave rectifier, how much is the value? No, no, no. VDC. 2 Vm by pi, na? No, not that. Im nahi. We have to tell me about VDC or V out average. So Im won't come there, na? V. But for half wave rectifier, for half, yes, it is Vm by pi. And for full wave, it is 2 Vm by pi, and here also it is same, right? Tell me about the RMS value. How much it is? RMS value how much? Here it is Vm by root 2, right? Vm by root 2, correct? Then efficiency, how much is the efficiency of half wave? These are some important points which you should know. How much is the efficiency? So around 40.5. Here it is 81.2. Here it is 81.2. Most of the points are similar. Then we have ripple factor. I think 1.21, right? 0.48 and 0.48. Correct? First one is half wave rectifier. Second one is center tap, full wave rectifier, and third one is bridge rectifier. So we have written 6 points. Remember, these are important, Now tell me PIV rating of the diode. How much is PIV rating for half wave? It is Vm. Here it is 2 Vm and here it is Vm. Okay, fine. Now there is something more which I haven't discussed now. Transformer utilization factor. Okay, so please write it down. We will be verifying it right now. It is around 28.7% for half wave rectifier, 69.3% for full wave center tap rectifier, and 81% for full wave bridge rectifier. So please note it down. Transformer utilization factor. So how efficiently the transformer used is utilized in conversion process. Alright. Then the ripple frequency is Fn. Here it is twice Fn and here it is twice of Fn, input frequency. Okay, so please note down these points. You can even add IDC and IRMS also, no problem. You can add IDC and IRMS also. In fact, I will be sharing a few videos on transformer utilization factor also, wherein we can view it properly. Okay, so can we go for the explanation of TUF now? Transformer utilization factor. Everyone written these points? Yes or no? All right. So this comparison is important. So might be in the exam VM will be given to you, and you need supposed to find VDC. Here ripple factor can be asked for all three. Transformer efficiency will be asked for all. So these type of questions are expected. Anyways, let's go to the. Hello, can you hear me? Hello, can you hear me now? Is my audio off? Hello, can you hear me? Okay, in between I got disconnected. Anyways, so let's begin with. Let's write down transformer. I think I have to open the document one more time. So write down transformer utilization factor. TUF. So it indicates how effectively the transformer capacity is used in delivering DC power to the load for the given AC power. Okay. So write down TUF formula. TUF is given by, it's the ratio of two quantities, which is first is DC power delivered to the load divided by AC power rating of secondary winding. AC power rating of secondary winding of transformer. Okay. All right. So tell me, in all the types of loads, what is the amount of DC power uh, obtained at the output, or DC power delivered to the load? PDC. It's actually called as PDC. It is DC power delivered to the load. How much is the formula given by? It's given by IDC square into RL. There are three formulas, na? Remember, VDC square upon RL, or VDC into IDC, or IDC square into RL. Agree? So this is formula number one. Please write it down. Where RL is the load resistor and IDC is the DC value of the output current. Okay, written. Now, usually, write down next. Usually, the transformers are rated for AC power. What do you mean by it? That means the AC power in transformer is specified in terms of volt ampere rating. You remember what was volt ampere rating? VA rating. Volt ampere rating. It's called as VA rating. So therefore the capacity of the transformer is always specified in terms of RMS value, because at the transformer input we have RMS value, and at the output also we have a RMS value only. Okay, it's a different thing, we converted into peak value, but it's fine. So let's say the transformer capacity is always specified in terms of RMS value of voltage, input voltage, that is VRMS, and current, IRMS. Okay, because this is my transformer. Let's say I'm drawing normal transformer, not the center tap transformer. Just a minute. Okay, yeah, this is a normal step down transformer. So this value they are saying, this input and output are both RMS only. So this is measured in RMS. Okay, present whatever the value present over here, either the current or the voltage, they are specified in terms of RMS value, not the peak value. Okay, and the product of VRMS and IRMS is the VA rating of the secondary of the transformer. So what is VA rating of secondary winding of transformer given by IRMS into VRMS? Agree? So what will be the power of the secondary winding of transformer AC? It is PAC. It is given by VRMS into IRMS. Agree? So first formula was PDC, IDC square into RL. Second formula is VRMS, IRMS. Call it equation number 2. Okay. So for the power at secondary winding, that is AC, is given by VRMS into IRMS. So what is TUF? Transformer utilization factor given by TUF is given by PDC upon P secondary winding AC power, that will be IDC square RL divided by VRMS into IRMS. This is equation number 3. Written. What is VRMS? So VRMS is the RMS value of the voltage at the secondary winding of the transformer, and IRMS is the RMS value of the current that is supplied by the secondary winding of the transformer. This is primary winding. This is secondary winding. Okay. So this is the generalized formula for TUF. Now let's find this value of transformer utilization factor for half wave rectifier. So can we start, everyone? Up till here you have written? Yes, no? Hello? Completed up till here? Okay. So now let's start with for a half wave rectifier. So TUF for half wave rectifier. Let's try and find out how much it is. So in case of a half wave rectifier, current flows to the secondary of the transformer only during the positive half cycle and no current flows to the negative half cycle. Do you agree to it? Hello? Okay. So that means if I have a half wave rectifier, what it says is, if I have this, so primary, secondary winding, this where this voltage is coming from, can you tell me? And output will be like this, right? Half wave rectified output. So here we have a transformer, we have a step down transformer to be precise. So here we have 230 volt 50 hertz. Yes or no? What is available at the output now? Output mein kitna hai? You have this kind of a waveform only, na? Sinusoidal only, right? And then you apply to the rectifier and the load RL. Then here after that you get what type of a waveform? Half wave rectified. Okay, तो हमें इसका rating चाहिए. We want the rating of the secondary. It's not half wave like this, it's full wave only. At the second, it is the secondary of the transformer, secondary winding. So at secondary winding, what is my value of VRMS? Tell me. Now this will be tricky. So in a half wave rectifier, transformer will supply secondary voltage of pure sinusoidal nature, right? This is sinusoidal in nature. This is like a sine wave available at the secondary winding. Okay. So what will be the RMS value of such a sinusoidal waveform? Do you remember? It's Vm by root 2. Yes or no? Or 0.707 times Vn. Are you following this? What I'm explaining? So at the secondary value, we don't have a sine wave. We don't have this half wave rectified output yet. Okay. Now next, the current supplied by the secondary winding of the transformer is a pulsating half wave. देखो ये voltage है. This is voltage. But what about the current which is flowing in this entire loop? Current is flowing for one half, not flowing for other half, right? So current in the current waveform will be looking like this. If I have current secondary RMS, the current waveform will be like this. Are you understanding? The voltage waveform was like this. There's a difference between the two. So here the current supplied by secondary winding of transformer is a pulsating half sine wave like this. Agree or no? Because current for one half cycle, for positive half cycle, this diode is on, so current will be there. For negative half cycle, diode is open circuit, so current will be zero. So current nature will be this. This is the current nature. So for this waveform, we have calculated na IRMS. Kitna hona chahiye IRMS? Can you tell me now? We have written into this thing also, table also. How much should be IRMS? IM by root 2 or 2? Half wave rectified. बताइए. Yes, perfect. It is IM by 2 for a half wave rectified. So here we'll write IRMS is IM by 2. Are you understanding? So now we calculate the power. So let's calculate the secondary winding AC power for the half wave rectified is given by IRMS into VRMS. How much is this? IM by 2, VM by root 2. Okay. So IM VM by 2 root 2. Let me call this 1.1. Agree? Now, PDC is given by what is the formula? IDC square RL. How much is IDC for a half wave rectifier? IM by pi. Okay. So here IDC square will be IM square by pi square RL. This is PDC. Let's call this equation 1.2. Now we have to find the value of TUF. Let's find the value of TUF. It is IDC square RL by pi square into IM VM by 2 root 2. So the 2 root 2 will go up. Correct? Now calculate this. How much is this? Oh, sorry. IDC square nahi. It will be IM square by pi square. Correct, na? Because TUF is what? PDC upon P secondary winding AC. Okay. So over here, what gets cancelled? Tell me. Yeah. VM gets cancelled. I sorry. IM gets cancelled. What else? What is IM? Yeah, I am into RL is VM, correct? So this is VM. These two quantities are VM into 2 root 2 divided by pi square into VM. So VM also gets cancelled. So it's 2 root 2 upon pi square. How much is that? Tell me. Half wave rectifier. So TUF for a half wave rectifier is how much? Tell me. 0.287. And in terms of percentage TUF, it will be 28.7%. That's what we have written in the comparison, right? For a half wave rectifier, see, 28.7%. Okay. So what does that mean? What does this 28.7% mean? Any idea? TUF is transformer utilization factor. So how much this transformer is actually, getting utilized is very less, 28.7%. This means that only 28.7% of AC power that will be supplied by the secondary winding of the transformer will be supplied to the load register. So there is a loss of more than 70%. Okay, understood the meaning of this? This is not very good for a transformer. So transformer is underutilized. Now we go for next one. TUF, sorry, TUF for full wave center tap rectifier. So let's find out that. So for a full wave center tap rectifier, um, how will be my secondary voltage? I mean, full wave rectifier. I have my like this, right? Center tap. I have the winding, and I take the center tapping over here. So here full cycle comes. Yes or no? And you have a diode. You have a diode. So at any one point of time, at least the diode is on, right? At least one of the diode is on. This is 230 volt AC. Yes or no? So RMS value of secondary here, VRMS will be how much? Tell me. Come on, tell me. VRMS कितना रहेगा यहाँ पे? What is the RMS value of sinusoidal secondary voltage here? It's Vm by root 2 na. And the current supplied by the secondary winding, this is secondary winding. It's a pulsating sine wave only na. So IRMS also will be Im by root 2. Are you following or no? Okay. Okay, because for a board the cycle, one diode is at least on. So there is no segment, I mean output is this way, right? And we have derived the RMS value of this waveform. How much it is? Im by root 2. Yes or no? And VRMS is Vm by root 2. So now we substitute the formulas. In the formulas, what is the IDC? It's 2 Im by pi. Okay. Now we use TUF, which is given by IDC square RL upon VRMS into IRMS. We substitute the values over here. So 2 Im by pi will be 4 Im square by pi square. Yes or no? Into RL. And VRMS is how much? Vm by root 2. So here Vm, root 2 will be above. And IRMS is Im here, root 2 will be above. Okay. Now what gets cancelled? Um, Im gets cancelled, and Im into RL is Vm only. So Vm also gets cancelled. This also gets cancelled. Yes or no? Let me just write this again. So it will be 4 into 2 by pi square into Vm upon Vm, because Vm is Im into RL. Okay. So Vm gets cancelled out. So what is TUF for a full wave center tap rectifier? How much it is? 8 by pi square, can someone calculate this? How much it is? 0.81 it is? Please, can you check? It should be close to 0.81. 0.81. Is this correct? So transformer utilization factor for a full wave center tap rectifier is 81%. That means what? 81% of the AC power that is supplied by the secondary of the transformer will be delivered to the load at the output. Okay. Oh, sorry, one mistake. Um, this is not for the center tap full wave center tap rectifier. It is for the bridge rectifier. Sorry, not for this. It's for the bridge rectifier where we have 4 diodes. Okay, so please correct this. Here we have 4 diodes, right? One here, one here, and you applied. Yes or no? So please make the correction. It is not center tap, it is bridge rectifier, full wave bridge rectifier. So for bridge rectifier, this formula is correct. So any one point of time, the secondary winding is, the secondary winding will be Vm by root 2. Here, the value of the current which flows is like this nature. So that will be Im by root 2. Here it is. Okay. So this is not for the full wave center tap, it is for the bridge rectifier. Extremely sorry for that. Bridge rectifier. So for a bridge rectifier, the transformer utilization factor is 81%. I realized that by writing the this thing differentiation. See, it's 81% over here, and that is full wave bridge rectifier, not the center tap rectifier. Completed. Okay. Now we go for TUF for full wave bridge center tap rectifier. Okay. So TUF for full wave center tap rectifier. Now full wave center tap rectifier is slightly different case. Here one, you have a secondary winding which has a tapping, and you have 2 diodes here, and load is resistive load. So this ground and this ground remains the same. This is input V in, which is 230 volt AC mains. So let's find out this. So in a full wave rectifier, the secondary current flows through each half separately in every half cycle. Yes or no? So if I want to plot diode 1 and diode 2, now if I want to plot ID1 and ID2, not the total current will be ID1 plus ID2. So IL will be ID1 plus ID2. What problem I am saying is, if one of the diode is off, this current will be 0, but ID1 will be there. Okay, so we get the total current IL. If diode 1 is off, ID1 will be 0. But what if we have individual, because these are the currents which are flowing through the secondary of the transformer. Yes or no? This is secondary of the transformer, and we are finding TUF rating, so we require secondary current. So if I plot over here two currents, that is ID1 and ID2, can you help me out in drawing how it will be? So this is current through diode 1 flows through positive half cycle only. Na? For negative half cycle it is off. Here it will be like this. And for ID2 it's positive half cycle it is off, negative half cycle it is on. Yes or no? So here D1 is on, D1 is on, here D2 is on. So this type of current is there, right? So in a full wave center tap rectifier, the secondary current flows through each halves in every half cycle separately, while the primary of the transformer carries the current continuously. Yes or no? So here if I want to see the primary current, okay, this is primary winding current. Here the current is continuous. Agree or no? Here the RMS value is continuous. So primary of the transformer carries the continuous current, whereas the secondary will carry discontinuous current. So TUF is calculated for primary winding also and for secondary winding separately. Do you agree on this? because both the currents are different here, because there is a discontinuity over here. Okay, whereas input primary TUF is different. So TUF over here, average value of full wave center tap rectifier will be primary winding TUF plus secondary winding TUF divided by 2. We do this last. Okay, now let's calculate secondary TUF. Secondary transformer utilization factor. What is the formula given by IDC square RL upon VRMS IRMS? Now tell me over here, what's the value of IDC for a full wave bridge center tap rectifier? 2 Im by pi. Correct? What is IRMS and what is VRMS? We have derived now for the secondary winding. How much it is? Im by root 2, and here it is Vm by root 2. So let's substitute these values. So secondary TUF will be 2. Acha, this will become 4 Im square by pi square into RL divided by Im Vm into 2. Root 2 is 2. So if you solve this further, this Im and Im gets cancelled. Vm into RL is Vm only. So this also gets cancelled. You get 8 upon pi square. We just now calculated na 8 upon pi square. How much is this? 0.81. So secondary TUF for a full wave center tap rectifier is 0.81. Okay. So now we will calculate the primary winding TUF. Are you following this? Have you written this? Before I go ahead. Okay. Completed up till here so that I can move ahead. Yes, no. Hello. Okay. Now write down and okay, this problem with the, yeah, now it's resolved. So in a full wave center tap rectifier, I think I have to open the document again. In a full wave center tap rectifier, the primary of transformer, this 1 degree is primary, actually called as primary of the transformer, is feeding two half wave rectifiers separately. Agree on this point? See here, if I see, if I see only this portion, what is this? This is nothing but a half wave rectifier, yes or no? And if I see this portion, this is again a half wave rectifier. So the yellow portion and the green portion are two half wave rectifiers, right? So we say that in a full wave center tap rectifier, the primary of the transformer is feeding two half wave rectifiers separately, and these two half wave rectifiers separately work independently of each other but fed a common load. Yes or no? And half wave rectifier ke liye we have already derived a TUF rating. So what is TUF for half wave for a half wave circuit given by 0.287? Yes or no? Arey, we have derived na half wave ke liye 0.287. So secondary TUF is 0.287, or, and now there are two halves, right? It's feeding two half wave rectifiers separately. So TUF for primary winding will be 2 into TUF of half wave circuit. So TUF for a half wave circuit is half wave rectifier actually. So it will be 2 into 0.287, which will be 0.574. And now we calculate average value of TUF for a full wave center tap rectifier. It will be what? TUF for a primary winding 0.574 plus for a secondary winding it is 0.81 divided by 2. So this average value is 0.693. Or percentage wise, TUF for a full wave center tap rectifier is 69.3%. That is what we have written. So please note it down quickly. So the best rectifier with our hand is bridge rectifier, which has the TUF rating of 81%. Here it is 0.69. I hope you are following this. Yes or no? Hello. All right. Now next part will be in your syllabus. Let me open it. Adding filter capacitor. So far we have covered in diode and application PN junction diode, application of rectifier, the yellow portion we have covered it, right? Then we have covered full wave center tap bridge rectifier with resistive load with the parameters such as ripple factor, rectification efficiency and transformer utilization factor. Agree or no? So we have completed all of that. Now filter circuits. Well, filter circuits, I guess I'll explain you with the help of my old PDF because that will take some time. Let me just go through the PDF. Let's see if you can understand it or no. Filter circuit. Let me check if I have my old PDFs. It should be there. Not a problem. Not this one. Mm, no, not these either. This will be required, but let me add over here and let me search again. I think it is there in 34. Let me search for a bit because if I have that PDF, it will be easier to explain filter topic. No, not here. Maybe it is capacitor filter. No, not here. 34A it is. Let me check. 35. Sorry. Someone wants to join the meeting. Okay, I'll admit them. Okay, this is the circuit. Capacitor filter. Can I start with the explanation, everyone? Just listen. I'm using my one of my old PDFs. You know so far, do you know the working of full wave center tap? Have you understood the working of full wave center tap rectifier? Yes or no? Tell me. Only with the resistor RL. Now we are adding the capacitor. That's the other story. But have you understood the working of full wave center tap rectifier? Now full wave center tap rectifier plus that filter capacitor becomes capacitor filter circuit. So with that knowledge, can I use this PDF and start or should I explain from scratch? Hello. Okay. So I'll use this PDF and explain you all. This I was used in last semester. So now, same working. So can you see these dotted lines? 0 to pi, 0 to 2 pi, 0 to 3 pi. Up till there, it's absolutely working fine. That means during the positive half cycle of the input, that is over here, Vi is positive. So what happens? Diode D1 turns on, and at the output you get a full wave rectified output. During the negative half cycle, the D2 turns on, and still you get a positive output only. Okay, so for a normal case, without the filter, your output should be like this. And you have understood. Now what do we want is, this contains a high value of ripple. Somehow we are connecting the capacitor. I hope you're following this. Somehow we are connecting the capacitor. Now capacitor, what happens? Capacitor charges instantly very fast and it discharges very slow. So your waveform will be like this here. I think you have verified this in one of the experiment also. So your waveform gets converted to like this. This is filtered output and this is rectified output. So that is what we want. It will smoothen down the output. Now the amount of ripple is only this much. Earlier it was this much. So amount of ripple means the AC component. So we are reducing the AC component in the circuit. And ultimately we want a constant DC. I mean for the supply from AC to DC conversion. Now let's see how this works. Understood this? What we want? We want the waveform to look like this with filter. This is with filter. With C filter. So I am starting the explanation now. Listen carefully along with this diagram. Okay. So now positive half cycle hai of the input. So this is positive with respect to this is 0 actually. This is grounded. Okay. This is positive. So point number A is positive, point number B is negative, and point number O is grounded. Okay. So for a positive half cycle of the input, diode D1 turns on. Normal thing will happen. So there is a RC circuit now, RC element, this R and this C. But what will happen is the diode will turn on and will start charging the capacitor. Okay, because the current starts flowing. So it will charge the capacitor from 0 till point A. Okay, let me use this different notations over here because A and B is already utilized here. Okay, so capacitor diode current will flow through the capacitor. It will charge the capacitor. Now capacitor will store the charge till how much maximum it will store. It will store till it will go from 0 and it will store till maximum value of Vm. Okay, so it will store till Vm value maximum. Now it has stored till Vm. Now after that what will happen? Now the input is falling down. Okay, input is reaches the peak value. Now it falls down. So now what will happen? Tell me. The capacitor is charging. Now what will happen is, whatever charges are stored inside the capacitor, now slowly what will happen? The diode D1 will remain turned on. Yes or no? Or it will remain, it will go off. See, diode D1 is on from 0 to A. What about A to B? Is it on? Hello? No, see, this capacitor, it cannot charge further, na? Till Vm it will charge. After that, this diode, whether it is on or off, I mean, whether it remains on in the positive half cycle from 0 to pi, right? But it cannot discharge or something, right? Through the diode only, because diode does not allow back current to flow. So what will happen is, these charges stored in the capacitor will be discharged via now RL. Okay, so discharge rate will be RL into C. We have a rate of charge and discharge, right? So for a positive half cycle, diode is on, it will charge the capacitor. For the same positive half cycle, the capacitor will be discharged like this. Okay, so there is a charging time period, there is a discharging time period. Alright, so why the charging is instantaneous and discharging is slow? So the capacitor will continue to discharge. It will reach pi. Now pi may diode D1 is off. Still the charges stored in the capacitor has not reached 0. So it will slowly discharge. Now why it will slowly discharge? Listen carefully. So what is the charging time? The charging period of the charging time given by R on of the diode, means on state resistance of the diode is very, very small. Meaning when the diode is on, it is offering some resistance, and that resistance is very, very small, 1 ohm to 3 ohm. And what is the capacitor value? Microfarad. So let's say your value over here is 100 microfarad. So RC time constant hota hai na, you might have heard it, RC time constant. So here R is R on of the diode because diode is turned on, and the capacitor value. So RC time constant is 100 micro into 1, that will be 100 microsecond, that will be 0.1 millisecond. Okay, and ये time period कितना रहता है for AC means? AC means के लिए कितना रहता है one time period? Tell me. अरे AC main means this ना. So what is one period given by for the AC waveform? It is 50 hertz, right? So time cycle will be 20 millisecond, right? And यहाँ पे मेरा half cycle ही मिल रहा है ना. I am getting half cycle only. Are you following what I am saying? I am getting half cycle. So half cycle is 10 millisecond. So this is 10 millisecond. And for a complete period, for around 0.1 millisecond, I mean this is 10 millisecond, agree? And हमारा time कितना charging time period? 0.1 millisecond. So it will, that's why it will charge instantaneously. It will charge instantaneously, quickly, very quickly. Because charging time constant is 0.1 millisecond and a one period is 10 millisecond. So we have a lot of time for a capacitor to charge. So it charges instantaneously. But now after point A, capacitor starts getting discharged via RL. So it will lose the charge slowly. Now when the discharging time period will be given by what? R, this RL and this C. Now this RL value might be, let's say 1 kilo ohm, and this C is around 100 microfarad. So when you multiply 1k with 10 microfarad, it will be 0.1 second. Okay. Now 0.1 second kabhi aayega in a 50 hertz signal? It will come after how much time? एक period अभी 10 millisecond का है. So how many cycles it will come next? 0.1 millisecond कभी तक पहुंचेगा? After 10 cycles ना? That means it should be 100 millisecond, right? मतलब ऐसे 10 cycle आएंगे, then it will completely discharge. Yes or no? This blue color is my capacitor voltage discharge value. So it will completely discharge after 10 such cycles. So 10 to आता नहीं है. Whenever it reaches over here, second cycle comes. So whenever this is discharging, it encounters another cycle. That is, now the diode D2 is turned on. Yes or no? And it will start charging in the same direction. Again, it will start charging the capacitor till Vm. So from A to B. Why it will stop at B? Because it is now the diode D2 turns on. So again the charge is getting stored in the capacitor. The capacitor will charge from B to C when the diode D2 is on. Okay, in a negative half cycle. So in a negative half cycle, the diode D2 is on and it starts charging in a positive way only and charges till C. Okay, after C, the capacitor again will try to discharge. Here it is, the volt, because the voltage is falling down. So capacitor discharges till point D. Again the diode D1 turns on. So here, see here, over here diode D2 turns on, not before that. See this. Over here the diode T2 turns on. Over here the diode D1 turns on. And again from D2 it start charging, and from E onwards it start discharging. So O to A, capacitor is charging. A to B, capacitor is discharging. B to C, capacitor is charging. C to D, capacitor is discharging. Then why such long periods? Why so slow discharge? Because of the discharging time constant. It is 0.1 second. And our period is around, हमारा period कितना चल रहा है? 10 millisecond का. When will you reach 0.1 second? After 10 cycles. So by the time you reach 10 cycles, no, it won't completely discharge. It will encounter the next cycle. Okay. That's why the waveform is like this, smoothen out. Yes or no? So actual waveform of the circuit is this. The yellow portion which I am highlighting. This. And then again it will charge. Again it will discharge. So it will depend upon the how fast and slow the capacitor is charging and discharging. So in this case the capacitor is charging instantaneously because the diode onset resistance is very small, and the diode is and for the discharging rate is very small. That's why this is slow. Discharge is slow, charging is fast. Okay, so this is the working of capacitor filter. I don't know how much you have understood, but little bit you have understood or no? Yes, no?
Yes.
I will be sharing with you capacitor filter document. Let me show it to you. There the working and all, everything is explained in words. See this? So here everything is explained properly. देखो ये. So here you can get the statements from here. Okay, is that fine? Now one last topic is remaining. The filter circuit is also over. There are various types of filter circuits, but you will only have a capacitive filter circuit. Actually filter circuits के प्रकार कौन से हैं? Let me also show it to you. The filter circuits are of 3-4 types. ये देखो, inductive filter, capacitive filter, inductive capacitive filter, LC filter or pi filter. So you have C filter only in your syllabus. Okay. So you know mathematically what do you mean by filter? You know the Fourier series पता है तुम्हें? You have done in mathematics Fourier series or something. Have you heard of Fourier series? You might have encountered in your 10, 12. How the Fourier series of this kind of a waveform, pulsating waveform is this. 2 Vm by pi, it is the DC component, and then we have minus 4 Vm by 3 pi cos 3 omega t or 2 omega t. So this is the AC component. So this AC component we want to filter out. That's why we require the filters. We want only DC component at the output. Output contains AC plus DC. So to remove this we apply filter circuits. Okay, or minimize the AC component. Okay. This is mathematical funda behind the filter circuit. So this is also I'll share it with you. Now in your syllabus we have Zener diode, construction, working, IV characteristics and voltage regulator. You want me to cover this now or later? So agree.